Yes, just a minute, please.
Okay, so it's an honor to present you. And now you give them the floor. Actually, you have the screen. So good lecture.
Let me see. Is this okay?
Yes,
Is it
it's
full?
okay. Just present.
I did, but seems that's not okay then. So let me share. Let me. I'm supposed to be sharing full screen now. Is it full screen?
Yeah, it's full screen. Just you need to click on presentation to put, yes, there. Click on that.
Okay then. So okay. So good afternoon, everybody. I'm gonna be quick because I have how many minutes, Henrique? Please.
Sorry, yes, you have 30 minutes. It's my error. Forgive me. You have 30 minutes because we have a audience today. So you have 30 minutes, and I will inform you when it's 10 minutes remaining. Okay.
Thank you. So thank you, everybody. Sorry not being so present, and it's good to hear Norbert's speech here. It's kind of good sounds to my ears. Nice presentation. Thank you very much, Norbert. And going straight to our presentation, here I'm on the first. I'm kind of not seeing what I'm presenting here, so I may need some help. I'm the title slide, isn't it?
Yeah, but it is still on the PowerPoint screen. You need to put in the presentation screen. Yes. Yes.
Now it is?
That's good. Yeah, that's good.
Okay. So this is about the recent advances in developing ionospheric scales index maps based on the tag map for South America. It's a two-paper publication last year. Several authors, myself, Giorgio Picanso, Paulo Barbosa Neto, Paulo Nogueira, Carol Carmo, Liza Rezende, Juliano Moro, Shen, Sônia Suchen, Esmeralda Romero, Regia Silva, and Cristiano Vrassi. All these guys helped somehow in the development of this work. What I'm going to present to you is a brief introduction, methodology for developing the Geeks map. Indeed, the Geeks is an index that has been an idea of Norbert that just present here. I'm just trying to help him to improve. And I'm going to show some results in discussion, which will be most of my talk, and then the conclusions and some acknowledgements. So again, this is a presentation on the two papers published last year, September 2020. They are published on Space Radar. The first one deals with the studies and applications, the development of the Geeks map for study and applications. And the second one goes to the examples that I'm going to show here. This is the journal where they are published. And if you contact me after the speech, I'll be glad to provide a copy of the paper if you don't have access to the journal. So this is to summarize. Basically, you have GPS degradation for the Sun-Earth connections. And it's a complex physics behind it. So what we're going to do is try to simplify the process. And not only me, several authors have done that. And we see since 1963, Briggs and Parkins, and then several other authors. I'm not going to listen, not going to read all this summary. This is in the paper, first paper of the both, the two that I presented here. So there is the name of the index in the left side. So you have S1. Normally people know S4. People, even if people doesn't work with ionosphere, they know what does S4 mean, but they never know that there is an S1, S2, S3. So they have several S's, have F index, ROTI is another one that people is studying, the W index, delta W, WB, AATR, it's a long arc.
Dr. Sorry to disturb you, but your presentation is in dual screens, like I am the presentation. You need to put in the public presentation. I'm seeing the presentation like you in two different screens, the next slide and the current slide. So you need to put in the public presentation. Could you do that?
Clésio, é só clicar em exibir configurações, o menu ali em cima, e você consegue exibir configurações. Lá em cima, nos menus de cima.
Ok.
Porque está aparecendo como se fosse para ti. O próximo slide e o slide anterior. Você tem que colocar para o público.
É que eu tenho 2 monitores aqui na minha sala.
Eu imaginei.
Então, você está no modo de apresentação para você, não para o público. E se você for
vai lá no exibir
configurações, clica lá.
Onde tem isso?
No mouse. Não tem a setinha do mouse? Ali em cima. Tem 3 menus: mostrar a barra de tarefa, exibir configurações e encerrar apresentações. Aí não.
Em cima do slide, Clésio.
No PowerPoint, Clésio. No PowerPoint. Em cima do teu slide Introduction no PowerPoint.
Um pouco mais para cima. Do lado, do lado.
Exibir configurações. Do lado direito.
Aonde? Aqui?
Não. Do lado direito.
À direita.
Próximo
à direita.
O próximo menu. Exibir configurações.
Acho que ele não está vendo.
Na mesma linha de mostrar barra de tarefas, exibir configurações. Na mesma linha. Vai com o seu mouse para a direita.
Não tem aqui nada.
Mas nós estamos vendo isso. Mostrar barra de configurações, exibir configurações. Encerrar a apresentação de slides.
O seu slide introdução, bem em cima do título introdução, segue reto para cima, tem exibir configurações.
Sobe.
Mais um pouco.
Não tem subir para cima aqui para mim, não está aparecendo nada para mim aqui.
Não?
Eu imaginei.
Então,
assim para de compartilhar e na hora que você for compartilhar, tenta compartilhar a sua segunda tela, que dá certo, ao invés da primeira.
Vamos ver se eu consigo fazer isso. As you wish. Ok.
Some technical problems, but no problem. I will put more time for Clésio.
So now how I get the first...
Fortunately, we have sense today, so we have time.
So sorry, mas eu acho que não vai dar não, viu?
Então até dá para assistir daquele jeito, só que tá pequenininha a letra, mas até dá, Clésio.
Is that okay now?
Agora sim. Perfeito. That's okay now. We can...
Do you see the mouse?
Yeah, that's perfect now. You can go on.
Okay, then. Let's move on. So this is the index that we were talking about. I was talking about S1, S2, S3, S4 from, let me put this, from Big Z Parking, 63. So they developed some index to study the degradation of the signal due to magnetic storms, the solar bursts reaching the Earth, and several others. One of the important ones is another important one are the ROTI, that are also here. There's an explanation what about the index is, who is the first author in the first paper that I could find out. And AATR also highlight, among the several others. So my talk here will be improving ROTI from Norbert. In 2006, he started this job, and this was the original version. He just presented a very interesting improvement. So move on. What we try to do? We try to improve, modify the original Geeks equation to incorporate equatorial plasma bubbles, traveling atmospheric disturbances, and other neutral atmospheric drivers in modulating the ionosphere, like the atmospheric gravity waves. So we are trying to do that instead of being responsive to the storms only. In this sense, we modified the original equation to this one here, which includes an alpha factor, coefficient alpha that intends to include this response to internal drivers, and then we need this kind of delta tag over tag, a kind of gradient of the tag, and the original delta tag that is from the original equation, but also a latitudinal variation of the, to incorporate the different effects of the ionosphere suffered by the ionosphere due to magnetic storms. So we have alpha associated with the ultra atmosphere and beta to deal with the distribution of the effects, latitudinal distribution of the effect of magnetic storms in the ionosphere that is different from different range of latitudes, and also to have a scale. So we use also beta to have a scale 1 to 5. And this is from the kind of maps that we use as input. With that equation, this kind of map, after several studies, we could reach this kind of information. So this is a Geeks map for South America. For Latin, indeed we can do for Latin America now. But this is for South America. So you see the response here, the high level of disturbances, not exactly centered in the Appleton anomaly, but mostly distributed according to the Appleton anomaly. This red line here, this black line here is the magnetic equator, and these are the latitudes and the longitudes covering the Latin America. And this is the Geeks scale 0 to 5 according to this scale here, meaning below 1 is quiet atmosphere, quiet ionosphere. 1 to 2 is weakly disturbed. 2 to 4 disturbed. 4 to 5 exceptionally disturbed, and plus 5, meaning we are not restricting the top level of our scale, but from the studies we could do, we determined level 4 will be the most extreme one. So when you cross our studies and a big storm reached that we could not include in our study, we may have Geeks higher than 5, so we'll be extremely disturbed. To include these internal drivers, I already mentioned, we have the plasma bubbles. So we try to start before including the plasma bubbles and TIDs, which we did not do yet. TIDs, for instance, and atmospheric gravity waves, but plasma bubble we did. We have studied how to represent the ionosphere in our data. How could be a reference day when we do the calculation? Do you remember that we have a quiet day? This term here in the equation, tech for quiet day. Tech, I mean the tech values along the quiet day. Which will be the quietest day? How do you represent that? So we choose 5. We study 5 methodologies, and we get that the 3-hour mean average for the quiet days will be the best one. This is the comparison. You have here the median average that has been originally used by Norbert in the first earlier stages of his job, which is a good one, indeed, but in our opinion, the 3-hour running average during the quiet days represents a little bit better the days for considering as a quiet representation. 1 hour will be, when you take 1 hour mean average, you see very sharp, but the fluctuations are here, and which these are the ones that we'd like to represent. So this may be, for instance, gravity waves. Gravity waves may be seen. People, Takahashi and others mention interaction between the atmosphere and the neutral atmosphere and the ionosphere. So we may lose some information if we go too low in or too high in resolution. On the other hand, if you go a little bit lower in resolution, you miss some information that can result in false positives like these ones here. In the 6 hours for CIG's Cachoeira Paulista, I think so. And IRI for sure is the worst choice. So do not use IRI for represent a quiet day, because they do not do that. They do not work in our latitude range. With that in mind, we went to the alpha, to developing the alpha coefficient. The alpha coefficient is the coefficient between the local midnight of the real measurements against the local midnight of the reference day. And when you average that, you have an alpha, which is the coefficient that gives you the idea of the amplitudes of the gradient versus the variation of the tech. But to do that, we had to look for plasma bubbles in the quiet days, because quiet days means quiet, magnetically quiet days, not necessarily atmospheric quiet day. So here's another, an example. This is a quiet day, and this is a tech measurement, as you can see here, along the days of November 2015, and we have a plasma bubble in this green area here. And this is a quiet, magnetically quiet day. So this day was discarded from the average, and we consider the other. So this is not our reference day. We pick another one, and this is how our reference day looks like, and then we average with our 3-hour running mean, and that's what we have. So this is to have an idea what we have improved so far, using only this approach for internal drivers. This is the original version developed by that equation in 2006. I know that Norbert has improved a lot, but in the original equation, that was what resulted. So you see here levels close to 1, while our new approach resulted to levels close to 3, meaning this bubble here, which has very low Kp, are detected. Not close to 1 means, remember, to our scale, below 1 is quiet, between 1 and 2 is weakly disturbed, but come on, plasma bubble is not weakly disturbed, not for the tech. You have huge signal scintillations. So we have that in our index. We reached level 3, so which means looks like much more realistic to the plasma bubble events, internal events, what we call internal events. And here you have a plasma bubble here. And then you don't see anything in the original version, then you see weakly disturbed in our approach. For the internal drivers, once you have the alpha coefficient defined, we went to the beta coefficient. I'm not going to read that. I'm going to skip and go straight to the map. What we did, we select several stations distributed in the magnetic latitude. This is a magnetic deep map. So you have latitude versus longitude. That's the South American. This is the 0 is the magnetic deep equator, and then they have +5, -5, and 5 to 5, 5 steps of 5 magnetic latitude. And picking all the magnetic latitudes, several samples, we study what was the effect of that storms from January, December, March, April, June, August, September, and November, with the sudden commencement at this time, minimum phase at the minimum level of the DST here, and the period analyzed was some days before the 7th January, we started in 4, this case here, up to 10, few days after this storm. So this is the period analyzed. So we perform, our group performed, all the authors working together, we performed and analyzed all this period, what happened with the ionosphere, with the tech, during the index longitudes, and that we discovered a kind of standard, which average is represented by the red balls here, and then you have the coefficient alpha, and which coefficient beta here, distributed in latitudes according to the sum of the Kp, giving an idea of how they distribute along the latitude. And you see that mid-latitudes, low latitudes, but around the crest of the aperture anomaly, the tendency is to be much more affected than the lower and higher latitudes. And this was, so the beta here was calculated, which what will be, responding the following question, what will be the beta that makes that magnetic storm, that extreme magnetic storm, intense magnetic storm, to be 5 in our scale? So I'll repeat again. What will be the beta that will make that equation provide Geeks equal 5 to extreme magnetic storm. So we did that for all the storms, and we average, and there you have. These are the points. The black points are for each one, and the red ones are the average. So you have this average behavior. So now you have the equation for the beta. Beta is latitudinal dependent. And with that equation in mind, spread to the several seasons of the year, we could not study what happened during quiet time and disturbed time. So we are now going to the results. So we built a Geeks map for South America, and that's what we have. This is, you see spots of Geeks happening here with a quite low DST level in a sequence of the Geeks maps. We can have it every 10 minutes, but I'm showing here in this kind 6 hours to show the evolution of the, as we go from positive, I mean nothing happening, no external drivers acting here, to going negative up to a extreme magnetic storm, and you see the response here. So you see the response to the magnetic response of the ionosphere, and you see, backing one slide back, you see the response of the neutral atmosphere acting here. So this is the capability of the Geeks now. With that capability in mind, we went to the internal drivers studies. Zenrique, how many time do I have, please?
About 13 minutes.
13.
13
okay.
minutes.
I'll try to finish in 10. So going to the internal drivers, what we did was that we selected quiet period here. So this is a very quiet period. I'm not showing the DST here, but the DST was about 0, around 0, and I show a sequence of every 1 hour of Geeks map. Again, I can show every 10 minutes, but I'm showing every 1 hour because of space in the slides here. So, and I selected here several ionoson stations here to compare ionoson stations and all-sky imagers. In the other slides, I'm going to show you all-sky imagers to compare, and you see plasma bubbles during quiet time. So, with that in mind, we look for what's happening in the ionosphere when the Geeks is high during quiet time. So we look for these days during plasma bubble, for instance, and you see Fortaleza Paulista, Campo Grande, and Fortaleza, Campo Grande, and Cachoeira Paulista, and you see the sequence of ionograms from 0, again, 1 hour step, 0, 1, 2, 3, 4, 5, and 6, UT, which means midnight, 11, 10, 9 o'clock, 1 o'clock in the morning, and 2 o'clock in the morning local time. And you see here height versus frequency of the ionogram for those who are not used to. And these patches that you see here, this scatter in the radio signal of the ionoson, especially in the lower frequencies, at what we call scatter due to plasma bubble scatter process internal of the bubble. And what you see is the trace of the ionogram is completely scattered. You have, and people that work with ionograms call it spread of the trace of the ionogram. This is a spread F, spread of the F trace of the ionoson. And then you have correspondence between certain points here. Let's say, pick this point in this Cachoeira Paulista here, and then you see some spread, and Cachoeira Paulista is in the middle of something here. And then as it evolves to 3 o'clock, you see that only here spread and close to Campo Grande, which is in here. So this small, teeny, tiny yellow level here was captured, kind of captured by this ionoson here, because we have 100 kilometers aperture of the antenna of the ionoson. So you see quite correspondence in these two graphs.
Dr. Klesio, 10 minutes remaining. 10 minutes remaining.
Excuse me?
10 minutes.
Excuse me? 10 minutes, thank you.
10 minutes.
Thank you. Okay. If you're not satisfied with that, we went far, because this date here was 15 March, was before the magnetic storm. We have a magnetic storm in March, but before the magnetic storm was very quiet. So the reviewers did not believe our data, so they have to go before. We went far before and far later the magnetic storm. In very, very quiet period along the month of February, before very few weeks before. So I pick a bubble in the São José dos Campos and a bubble in Cachoeira Paulista, and you see those who are familiar with airglow imagers can clearly see a bubble crossing all these images here. Even in here with some clouds, you can barely see a bubble crossing here, which is this bubble here, even if it's cloudy. And then here too, you see these black traces here are bubbles in Cachoeira Paulista, but are not crossing the whole city. This is north, south, east, west. You cannot see crossing the view of the field of view of the lens of the imager, but they go a little bit northern, and then later in the night they go along as the time goes by in this direction here. It reaches and grows in altitude in the equator, and then it maps to the low altitude, and then you see clearly in Cachoeira Paulista, as we know from the physical behavior of plasma, equatorial plasma bubbles, and they cross completely the whole length, and you see a clear, well-developed plasma bubble here. And then you see everything here again. And you see here, Cachoeira Paulista is here, this again is South America, this is the magnetic equator again, and you see plasma bubble here, and you see the effects being detected by the Geeks maps, and patches, look at this, patches, conjugated points. So we don't see here because you don't have imaging there, but we have a bigger coverture. So we may, and we know for the physics of the plasma bubbles that bubbles are field aligned. So this is perfectly, and when you look here, you see they're perfectly field aligned, and again here, perfectly field aligned. So it seems that our Geeks works. And this is far behind, and then again, to confirm that we, besides having the optical observation, we went to the radio observation using ionosones, again, for the same stations, Boa Vista, Fortaleza, Campo Grande, and Cachoeira Paulista, and you see the bubble crossings here. And you see the bubble developing not here, but here later in Cachoeira Paulista, which matches, when we look here, it matches, I'll back one slide, it matches with this sequence of slides here. So bubble very north part, and then growing up, later, almost close to the end of the night, you see the bubble well developed. Again, later, quite later in the night to almost end of the observation time, you see the bubble developed in Cachoeira Paulista. And again, nothing, Cachoeira Paulista is here. And goes. Cachoeira Paulista get involved in disturbance, but not really touched by that disturbance. And only later in the night, you see very patches over Cachoeira Paulista here, and somewhere here. And then it's kind of related to this kind of disturbances. And again, you see disturbance close to the equator, and again, you see the mapping across the equator related to the magnetic field lines. Other day that we picked to show the quality of the Geeks maps for the quiet period was far after the magnetic storm of March 15. So again, this is a quiet period again. I'm not going through this because I would like to show the disturbed period, and I'm running out of time. So this is again, I'm sorry for the quality of the image, but that's life. We deal with data. Data sometimes goes bad. So this is a cover with a cloudy day here in Cachoeira Paulista, but fortunately we have bubbles in the northern part, and then we have bubbles here, see, again. And this is again another quiet period, close to 0 DST, and this is again ionosone confirming the observation that we had in the owl sky image. So very precisely described in terms of data showing the results of the bubble there. Now we go to external drivers. With that, Geeks develop, showing that Geeks works well and fine for quiet period. meaning magnetically quiet period, not ionospherically quiet period. So Geeks respond to internal drivers, which I just showed. Now we're going to external drivers, which are magnetic storm. And this is the kind of. The magnetic storm that occurred in 16, 17, I think, early in the 17, and went through the day, reaching the maximum in the 18th of March 2015. And you see no bubbles here, but some spread in the data. Again, Fortaleza, Campo Grande, and Cachoeira Paulista. And this is the Geeks maps, as I already shown in the previous slides. And something that I'd like to show here is the Geeks, okay, Geeks respond well, but the question is, why you have this kind of Geeks here, spread F here in this Campo Grande, and then an F3 trace here. When you have, we know that, by the way, just for the record, DST in this storm was 223 nanotesla negative. In this complicated scenario that we know, we have prompt penetration. Prompt penetration from the magnetic storm, from the external drives, and also we have disturbance dynamo electric fields acting there from the paper of Abdul that shown a very nice comprehensive study on that. With that complicated scenario, we see a spread F here that may or may not be associated with plasma bubble. Unfortunately, we don't have all sky images to confirm that, but may or may not be associated with plasma bubble. But spread F usually is associated with plasma bubble up to certain level. But for sure, we are experiencing some development of some irregularities. This is not a plasma bubble, at least it's a development of a plasma irregularity. For having a plasma irregularity, we have to have the lift of the ionospheric storm, meaning some electric field is lifting up the ionosphere at that time, which is indicated in this up corner here, 9:30 UT, which is just before sunrise. And this is after sunrise. The last line here is after sunrise. This is 7 o'clock local time. And then you have the disappearance of the irregularity, but you have a F3 layer. With F3 layer, you know also for the physics that F3 layer is the rising of the F2 layer, improving the quantity of O plus in the upper portion and keeping ionosphere being burned and increasing there by the solar radiation, increasing the density, and then you have the F2 being built again. So you have the F2 being built by the new photoionization that arrived, and the F3 is as a result of the lift of the layer, meaning that something is lifting through this hour here, something is lifting the ionosphere. Again, I'm just about to finish, I'm just showing the conclusions, but we know that Mansilla 2019 reported prompt penetration, he reported FOF2 disturbances, negative indeed, FOF2 disturbance after the storm commencement in the mid-latitudes. Mansilla in 2019, I think so. Meaning that something is disturbance, he associated that with prompt penetration. And we also know from the studies of Ferger, I think so, that different mechanisms may act. Disturbance dynamo and usually acts prior to the magnetic storm, the sun sunrise, while the prompt penetration may act after the sunrise. Or the contrary, I forgot a little bit. I think so. Anyway, then we have a transition here. We have a transition of operating mechanisms here. When you have the storm happening here, you have the transition from the disturbance dynamo electric field and prompt penetration electric field. In exactly what we measure here. And that this region, Campo Grande, was here in the middle of the map. So we capture this information especially when we have the interference of the magnetic storm. Meaning that even if we don't have plasma bubble here, but we have some, not bubble indeed, we have plasma irregularities, I can say for sure. We have disturbances here that are detected. So here, what we measured was a combining information of this plasma disturbances that are happening here with the FO negative phase of the FOF2 measured by Mancilla and the authors in the same period. I think that Batista also published something in 2017 on that. And Romero Hernandez also published something in 2018 related to this storm here. So showing that Geeks is completely reliable. And it serves as a simplification of the information to users of space weather, meaning if you are traveling with your airplane from Porto Alegre, which is here, for instance, you may experience nothing. But when you enter this zone here, let's say you are traveling to Manaus, which is about here, you are entering this zone, the pilot would probably experience some disturbance. Those planes that are entering here, because it's a three-dimensional, remember it's a time involved as well. So it's a three-dimensional, latitude, longitude by time. So you have to be there at the exact moment. So planes that are entering here are experienced, where planes are not experienced at the same time, at the same storm, at the same region of the world. So besides that, it's also a tool for doing science. So now you can see what you cannot see here from the Ionoson, for instance. You see that you have 3 stations, but you do not cover the whole Latin America. So we probably, if you had a Santa Maria station already working at that time, we probably won't see anything here in Santa Maria. So with that, we can extend the information that we have from our instruments. So having studies in the Ionoson may take advantage of the use of Geeks to improve the studies of the ionosphere with these indexes. Besides being used for the society, it's also useful for science. With that, I'm going to the conclusions, saying that we have helped develop the new index. And when I say we, it's all that guys in the beginning that really, really worked hard to get to this point. We investigated the deviation of the ionosphere content from the background pattern, and I show you here that we used the 3-hour running average, and we discovered that it's best for us. During magnetic quiet time, we revealed some patches during this patches in the atmospheric conditions, revealing disturbed and weakly disturbed ticks over here and there, and they are here and there, and they are related to the range and frequency spread F. Frequency spread F is the spread of the end of the trace of the F region. The Geeks map show the transition from higher values to the Geeks covering broad area in the South America, broader than the crest. Southern portion of the deep equator show the transition from the currency spread F at 8 o'clock, and explain it by the disturbed electric field acting in the period of analysis, causing bubbles and F3 layers. So we have transitions from. I'm not sure if I can say. I'm not completely sure. I'm a bit sure, but I'm not completely sure if I can say that it was a bubble. But I can sure say it was a plasma irregularity happening at that time that transit to F3 layer formation, meaning something is pushing the atmosphere, the whole ionosphere up. Despite the good results, again, we need to perform broader studies to determine the variation of the alpha coefficient with solar, with season, solar flux, magnetic disturbance. So there's a bunch of studies to do to improve the Geeks coefficient, the Geeks maps. We should include also effects of the South American magnetic anomaly, proximity to the auroral, and eventually equatorial electric jets. We have to study in deep these events there. To really be sure that the Geeks really works properly. But we know that it works okay, and we are gonna this or next first improve even more the accuracy of the index. There's also a need for a comprehensive studies the influence of plasma bubbles in the tag concerning the depletions and durations as well. Nobody did that. And we have 2 studies doing one PhD study, students doing research on that, and we hope to have more engaged in the future. If you want the data we have user free, just access www.imp.br/spaceweather and access the data for free. And thank you for the Embrace program for providing the data for us. And with that, I would like to thank the organizers for this event. SBGEA is always a pleasure to be here. Thank you for the chairs of the session, and thank you for SNPQ, for scholarship and research productivity, for the Developing Act that helped build the Space Weather Program, and for the Space Weather Program for providing the tech data, which are collected also by SBGEA, another institution in Brazil. Thank you very much. I'm now open for the questions.
Thank you very much for your very nice and interesting presentation, Dr. Clésio. And we are out of time, but there are some very simple questions here. I think no problems in address that. So let me ask the first one from Professor Eurico de Paula, concerning about the beginning of your presentation. Is the strong dips in the north due to the lack of data?
This one here?
Dr. Eurico?
Yes. For instance, yes.
Not really. The lack of data was here, not in this area. If you had a red dot here in the border, I would assume that will be lack of data, so we'll have some sharp gradients here, may cause some interference. But as you can see here, we have a blue point here, very clear information that low. And also, this information from that area here give me confidence to show that there is a continuity information going through this area, which is related to the Appleton anomaly, the crest of the anomaly, which is, as we know, mapped mirror in the northern and southern hemisphere, and due to the magnetic declination, they are closer to the deep equation in the northern than here. So I don't think so. I don't think that's there.
But I believe there are no stations in this region. There are no receivers in this region, so probably this is an artifact during the Geeks methodology calculation. Probably. I'm not sure, but probably. Okay, thank you.
Okay. And another question, Dr. Clésio, is from Dr. Inês Batista. And she's asking, was there all sky major in São José dos Campos in 2015? Maybe it should be São José do Cariri, right?
São José do Cariri. Sorry, if I say São José dos Campos, I'm sorry.
São João do Cariri.
São João do Cariri. I'm sorry. This is wrong. Thank you very much. That's why I love Inês. Inês is always very helpful. Thank you very much. This is wrong. This is not São José dos Campos. This is São João do Cariri. Thank you. This is the northern station here. São João do Cariri here. São João do Cariri. And the other station here is in Cachoeira Paulista. These two are the all-sky imagers. I wrote wrongly here, São José dos Campos. It's not São José dos Campos. This is São João do Cariri. Thank you very much, Inês.
Okay, thank you, Dr. Inês, for the correction. And the last question is from Norbert Jakowski, Dr. Norbert Jakowski. How you did define the Dix scale?
That's a great question. I knew that something good would come from Norbert. The level 5, Norbert. Let's come back to the scales here. The level 5 was defined by the storm. So the 5 is the highest level we can have based on the study we could reach. The more magnetic storm we could take it, we used to do the studies. And then we realized that 4 would be, that would be the beta, and beta has a latitudinal dependence with the storm. Beta is related to the storm with a latitudinal dependence, and several betas will give me a function between the function of latitude and season of the year. That said, we established level 4. The other levels were established based on our experience. This is something that should be addressed as well. My idea is now look for, okay, I have this beta 4, I have this preview study, so I have the zero model, the 0 level model. With that in mind, I can pick, for instance, all the plasma bubbles that occur prior to midnight and study what are the effects that they are causing in the jigs. And establish, for instance, that, okay, if they reach level 2, I can say level 2 is bubble, pre-midnight. So this is the study that we should pursue now. But to really answer your question, the intermediate level, the quiet is okay. We define based on our experience. No, nothing's happening. The extreme disturbance was also developed by our study, but the 3 intermediate levels were based on our look of the data, and not in was kind of empiric definition, not precisely defined. To define better that, we can have studies on specific events like I mentioned, gravity waves, CIDs, plasma bubbles, acting in the ionosphere, and then you can have the proper scale. So this is a tentative scale to start the job.
Okay, and now the last one, also from Dr. Norbert. Concerning the bubbles, could you estimate the spatial extension? Is this comparable with air glow observations?
I can see some. I have some bubbles here in some. The extent of the bubbles. That's a tricky question, Norbert. It's a good one again, but it's a tricky question because as you can see here, crossing, I can see it. If you have a movie, as I have, you can see it slightly moving westward, eastward, slightly moving, slowly from this one to this one, they move a little bit, a little bit, a little bit. And they keep the size. But the coverage, I don't know if I say the amplitude or the coverage of the lens, of the aperture of the lens, of the owl sky, I'm not sure if they can be compared to the aperture that I have here. Because when I look to the map, I kind of looking from the sky. I'm looking as I'm geostationary satellite looking down. So I can see much greater scales here in the Geeks maps than I can see here in the owl sky imagers. So I'm not sure if I can directly compare that. But anyway, that's a good question.
So, okay. Thank you again, Dr. Klesio, for such nice presentation. And my apologies for the audience. So it was very interesting. That's why I gave more time to Dr. Klesio. And now we need to move on for Dr. Fabiano. Dr. Fabiano, are you there? Fabiano Rodrigues?
Yes, I'm here.
Oh, thank you. Could you share your screen, please?
Yeah, just a second.
And now the last presentation in this afternoon is from Dr. Fabiano Rodrigues from University of Texas at Dallas. And this talk is titled AMISR14 Studies of Low Latitude Ionospheric F Region Irregularities. So, Dr. Fabiano is with you.
Can you see my...
I will advise you when remaining 5 minutes. You have 15 minutes, okay?
But I thought that if the talk is interesting, you're going to give more time.
For sure.
So if you don't give me more time, that means it's a boring presentation, isn't it? Okay. All right. So can you guys see my screen now?
Yes, we do.
Yes.
All right. So what I'm going to talk today is a study is a little bit different from what Norbert and Clasio talked about. They looked at indices, but they are all related to a space weather. I'll be talking about low latitude atmospheric averaging irregularities being studied with a system called A-14. This is something that I wanted to talk more about recent observations at this point, but due to the pandemic and some of the issues we had with the additional repairs that we had to make in the system, we were not able to make new observations to present at this point. So I'm going to have to go back to some of the observations that I already have to present it to you, and some of the things I've shown in the past as well.